Hello there, and welcome to AR Calm Science. Tonight, we're lifting our eyes upward, away from the glow of screens and streetlights, into something that is watched over every single night humanity has ever lived through: the night sky. Long before clocks, before calendars, before anyone had a name for a single star, humans lay on their backs in fields and on hillsides and stared upward into that same dark scattering of light. Tonight, we will explore what that darkness actually contains, the physics of starlight, the impossible distances involved, the quiet mechanics of a universe that has been unfolding since long before anything alive existed to notice it. We will talk about stars being born and stars dying, about light so old it left its source before humans existed, about the moon's strange relationship with Earth, and about how looking upward has shaped nearly every culture that has ever lived beneath an open sky. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is settle in. Let your shoulders soften, let your breathing slow, and allow your mind to rest into stillness as we explore the hidden science of the night sky together. Let's begin. Every star you see is not where it currently appears to be, because you are looking at old light. Starlight takes time to travel, sometimes an extraordinarily long time, which means the light entering your eyes tonight left its source years, centuries, or even millennia ago. You are never looking at a star as it is right now. You are looking at a kind of fossil, a preserved moment from the star's past, carried across space at the fastest possible speed, and arriving only now, tonight, to reach the back of your eye. Some of the stars scattered across the sky above you may have already changed dramatically since that light departed, grown larger, dimmed, or in rare cases, ceased to exist altogether, their final light still quietly completing its ancient journey toward Earth. The night sky, you see, is filled with stars so far away that distance itself becomes difficult to imagine in ordinary terms. Astronomers measure these distances in light years, the distance light travels in a single year, roughly 6 trillion miles. The nearest star system beyond our own sun, Alpha Centauri, sits about 4.2 light years away, meaning its light takes over 4 years just to reach us. Many of the stars visible on a clear night are far more distant still, their light having traveled for hundreds or thousands of years before finally reaching your eyes tonight. These numbers are so large, they stop feeling like measurements and start feeling more like a kind of poetry, an attempt to describe something the human mind was never quite unfolds across timescales that dwarf anything in human experience. Hundreds of thousands to millions of years from the first gentle collapse to the star's first true light. Somewhere in the sky above you right now, this exact process may be quietly unfolding, a star being born in complete silence and darkness, its light not yet ready to reach anyone at all. The color of a star reveals its temperature, with blue stars being hotter than red ones. It might seem intuitive to think red represents heat and blue represents cold, since that is often how we describe fire and ice in daily language. But with stars, the relationship works in reverse. The hottest stars burn with a blue-white light, their surface temperatures reaching tens of thousands of degrees, while cooler stars glow with a reddish or orange hue, their surfaces measuring only a few thousand degrees by comparison. Our own sun, a yellow-white star of moderate temperature, sits comfortably in the middle of this scale. Learning to read color as temperature transforms the night sky into something closer to a thermometer scattered across darkness, each twinkling point quietly reporting its own inner heat through nothing more than the color of its glow. Some of the stars visible in the night sky no longer exist, though their light is still arriving. Because starlight takes so long to travel, it is entirely possible, even likely, for a star to have already died, collapsed, or exploded by the time its earlier light reaches Earth. In such cases, we are looking at a kind of ghost, a final visual message the star sent out before it changed, still completing its journey across space long after its source. The source has transformed into something else entirely, a stellar remnant, a black hole, or simply darkness. This means the night sky is not just a picture of what exists right now. It is a layered composite of past moments arriving at different times, from different distances, some current, some ancient, some representing objects that technically are no longer there at all. The Milky Way, the pale band sometimes visible stretching across a truly dark sky, is actually the edge-on view of our own galaxy. From Earth's position inside one of the Milky Way's spiral arms, looking toward the galaxy's dense central disk produces that faint, hazy band of light stretching across the sky, made up of the combined light from millions upon millions of individual stars, too faint and too close together to distinguish separately with the naked eye. In areas with minimal light pollution, this band can appear remarkably vivid, a soft river of light cutting across the darkness. What you are seeing, essentially, is a sideways glimpse into the structure of your own cosmic home, an enormous spiral collection of stars, gas, and dust that includes our sun as just one small member among hundreds of billions. A single galaxy, like our own, may contain hundreds of billions of stars, a number the mind struggles to fully process. The Milky Way alone is estimated to contain somewhere between 100 billion and 400 billion stars, depending on the specific survey and estimation method used. Each of those stars represents its own point of light, its own history, and in many cases, its own system of orbiting planets. And the Milky Way is just one galaxy among an estimated 2 trillion galaxies scattered throughout the observable universe, each containing its own staggering population of stars. These numbers are less something to be calculated and more something to simply sit with quietly, letting the scale wash gently over you, rather than trying to hold the full enormity of it in conscious thought all at once. The moon does not produce its own light, but reflects sunlight back toward Earth. Unlike stars, which generate light through internal nuclear processes, the moon is simply a rocky body reflecting light from the sun. Its glow, sometimes bright enough to cast shadows on a clear night, is entirely borrowed, sunlight bouncing off its dusty gray surface and traveling the roughly 238,000 miles to reach Earth. This is why the moon's appearance changes shape throughout the month, not because the moon itself is physically changing, but because our view of the sunlit portion shifts as the moon orbits Earth, sometimes showing us a full, illuminated face, sometimes a thin sliver, sometimes nothing at all. in a slow, steady rhythm that has quietly marked the passage of time for as long as humans have been watching. The moon's gravitational pull is responsible for most of Earth's ocean tides. As the moon orbits Earth, its gravity tugs gently on the planet's oceans, creating a bulge of water on the side of Earth facing the moon, and a corresponding bulge on the opposite side due to the physics of the two bodies orbiting their shared center of mass. As Earth rotates beneath these bulges, coastal regions experience the rising and falling water levels we recognize as tides. This means the quiet, distant presence of the moon in the night sky is directly connected to something as immediate and physical as the ocean moving in and out along shorelines around the entire planet. A gentle daily reminder that celestial bodies, even at great distances, remain in constant, tangible conversation with life here on Earth. The moon is very slowly drifting away from Earth, moving outward by a tiny amount each year. Precise measurements, made possible by reflective panels left on the lunar surface by past missions, have shown that the moon moves away from Earth at a rate of roughly 1.5 inches per year, a consequence of the same tidal forces that create ocean tides, gradually transferring energy between Earth and the moon in a way that pushes the moon into a slightly wider orbit over time. While utterly imperceptible on any human timescale, this slow drift means the moon our distant ancestors saw was very slightly closer than the one we see tonight, and the moon future generations will look up at, millions of years from now, will appear very slightly smaller and more distant than it does to us. Stars twinkle, not because of anything happening at the star itself, but because of Earth's atmosphere. That familiar shimmering, flickering quality of starlight, called scintillation, occurs because starlight has to pass through layers of Earth's turbulent atmosphere before reaching your eyes, and as it does, it gets bent and distorted slightly by pockets of air with different temperatures and densities. This constant, subtle bending causes the star's light to appear to flicker and shift, even though the star itself is shining with a perfectly steady light far above any atmospheric interference. Planets, by contrast, typically twinkle far less than stars, because their proximity to Earth means they appear as tiny disks rather than true points of light, averaging out much of the atmospheric distortion that makes distant stars shimmer so visibly. Not everything you see moving across the night sky is a star or planet. Some are human-made satellites. Thousands of artificial satellites currently orbit Earth, and on a clear night, particularly shortly after sunset or before sunrise, when sunlight can still reach objects in orbit, even though the ground below has gone dark, some of these satellites become visible as steady, slowly moving points of light crossing the sky. Unlike the twinkling, essentially fixed positions of stars, satellites move in a smooth, consistent path, sometimes taking several minutes to cross from one horizon to the other. Watching one quietly slide across the darkness offers a strange, layered kind of wonder. Human technology, orbiting silently, visible against the same ancient backdrop of stars that existed long before humans ever built anything capable of joining them up there. Constellations are not physically connected groupings of stars, but patterns created by perspective from Earth. The stars that form a recognizable constellation, like the Big Dipper or Orion, often have no actual physical relationship to one another. They may be positioned at wildly different distances from Earth, sometimes differing by hundreds of light years, and have no gravitational connection binding them together in any meaningful astronomical sense. The patterns exist purely because of our specific vantage point from Earth, a kind of cosmic optical illusion created by chance alignment. If you could travel far enough in any direction, the familiar shapes we have named and storied for thousands of years would distort and eventually disappear entirely, revealing that the connections we see were never truly there in space itself, only in the particular angle from which we happen to be looking. Many constellations have been recognized and named by cultures across the world for thousands of years, often independently. Long before any shared global astronomy existed, cultures separated by vast distances and centuries of time frequently identified similar patterns in the night sky and built their own stories, myths, and navigational systems around them. While the specific names and stories differ dramatically between cultures, the impulse to find pattern and meaning in scattered starlight appears to be something close to universal. This suggests something quietly profound, that regardless of geography, language, or era, humans have repeatedly looked upward into the same essential darkness and felt a similar pull to organize it, to name it, and to weave it into the deeper stories of their own lives and communities. The North Star, Polaris, appears to remain nearly stationary in the sky, while everything else rotates around it. This occurs because Polaris happens to sit almost directly above Earth's northern rotational axis, meaning that as Earth spins on its axis each day, Polaris remains roughly fixed in position relative to an observer in the northern hemisphere, while all other stars appear to trace circular paths around it throughout the night. This apparent stillness made Polaris an invaluable navigational tool for centuries. Travelers, sailors, and explorers could determine true north simply by locating it in the sky, a fixed point of reference in an otherwise slowly rotating dome of stars, turning steadily overhead throughout every night across. As it slows, this means the star currently closest to true north, Polaris, has not always held that position and will not hold it indefinitely. Thousands of years ago, a different star occupied that role, and thousands of years from now, an entirely different star will take Polaris's place as the fixed point travelers gaze toward. Even something as seemingly permanent as the North Star is, on a long enough timescale, simply part of an extremely slow, ongoing cosmic rotation. Shooting stars are not stars at all, but small pieces of debris burning up in Earth's atmosphere. What appears as a brief, bright streak across the night sky is typically a small particle, often no larger than a grain of sand or a small pebble, entering Earth's atmosphere at extremely high speed and heating up through friction until it glows brightly and burns away entirely, all within a fraction of a second. These particles, called meteoroids before they enter the atmosphere, and meteors once they begin burning, often originate from comets or asteroids that have left trails of debris scattered along their orbital paths. Despite their brief, dramatic appearance, most shooting stars involve objects smaller than a fingertip, tiny fragments of ancient space debris, providing one of the night sky's most immediate and visually striking reminders of the universe's constant, quiet activity. Meteor showers occur predictably each year because Earth passes through the same debris trails left behind by comets. As comets travel through the solar system, they shed trails of dust and small particles along their orbital paths. When Earth's own orbit intersects one of these debris trails at roughly the same time each year, the increased particle density produces a noticeably higher number of meteors than usual, a meteor shower. Because Earth's orbit is highly consistent and predictable, astronomers can forecast meteor showers with remarkable accuracy, often years in advance, allowing observers to know exactly when and where to look for an increased chance of seeing shooting stars streak briefly across the darkness above them on specific nights throughout the year. Some stars you see in the night sky are actually two or more stars orbiting closely together, appearing as a single point of light. These are called binary or multiple star systems, and while some can be distinguished as separate points with sufficiently powerful telescopes, many appear to the naked eye as a single ordinary star. It is estimated that a significant portion of all stars in the galaxy exist within these multi-star systems, rather than as solitary stars like our Sun. This means the night sky likely contains far more individual stars than what appears to the unaided eye, many hiding in close gravitational partnerships, quietly orbiting one another across distances and time scales that render their true multiplicity completely invisible from Earth, without specialized equipment to reveal it. The night sky looks different depending on where on Earth you are standing, with entirely different constellations visible from each hemisphere. Because Earth is spherical, observers in the northern and southern hemispheres see substantially different portions of the sky, with only a narrow band near the equator offering views of stars visible from both hemispheres. This means someone standing beneath the night sky in one part of the world may be looking at an almost entirely different set of stars and constellations than someone standing beneath what feels like the same sky on the opposite side of the planet. The night sky, in this sense, is not one single shared experience, but a vast, varied dome that changes meaningfully depending on exactly where beneath it you happen to be standing. Light pollution from cities has dramatically reduced how many stars most people can see today compared with earlier generations. Artificial lighting from urban areas scatters into the atmosphere, creating a persistent glow that washes out the fainter light of distant stars, meaning city dwellers today often see only a small fraction of the stars that would have been visible from the same location a century or more ago, before electric lighting became widespread. In heavily light-polluted areas, only the brightest handful of stars may remain visible at all, while truly dark rural locations can reveal thousands. This growing disconnect between humanity and the visible night sky represents one of the more understated, gradual losses of modern life, an ancient, universally shared experience slowly fading from daily reach for a significant portion of the world's population. Some stars are so massive that if placed where our Sun currently sits, their outer edge would extend past the orbit of Jupiter. These are called supergiant stars, among the largest known objects in the universe by physical size. One well-known example, the star UY Scuti, is estimated to have a radius roughly 1,700 times that of our Sun, meaning its sheer physical volume dwarfs anything in our own solar system, almost beyond comprehension. Stars of this scale represent one extreme end of stellar possibility, reminding us that the Sun, itself an enormous object by any everyday human standard, is in truth a relatively modest, unremarkable star when measured against the far more extreme scales that exist scattered throughout the wider universe. When massive stars reach the end of their lives, they can explode in a supernova, briefly outshining entire galaxies. A supernova represents one of the most violent and energetic events known in the universe, occurring when a massive star exhausts its nuclear fuel and undergoes a catastrophic collapse,
followed by an enormous explosive rebound. For a brief period, sometimes just days or weeks,
a single exploding star can outshine the combined light of every other star in its host galaxy. These explosions also play a crucial role in seeding the universe with heavier elements, elements that eventually become part of new stars, planets, and ultimately, the very atoms that make up living things. Meaning much of what constitutes your own body may trace its origin back to the explosive death. The death of ancient stars. The elements that make up your body, aside from hydrogen, were forged inside the cores of stars that lived and died long before our solar system existed. Nuclear fusion inside stars gradually builds heavier elements from lighter ones, and the most massive elements are produced specifically during the violent final moments of a star's life, particularly during supernova explosions. When these stars eventually scattered their material back into space, that enriched matter eventually became part of the gas and dust clouds that later formed new stars and planetary systems, including our own solar system and Earth. This means the carbon, oxygen, calcium, and iron present throughout your body were quite literally forged inside the nuclear furnace of long-dead stars. A genuinely humbling reminder that you are, in a very real physical sense, made from stardust. Black holes are regions of space where gravity is so intense that not even light can escape their pull. When certain massive stars collapse at the end of their life cycle, the remaining mass can compress into an incredibly small, dense point, creating a gravitational field so powerful that anything crossing a certain boundary, called the event horizon, becomes permanently trapped, unable to escape regardless of speed, including light itself. This is why black holes appear entirely black. They do not emit visible light of their own, and any light that ventures too close simply disappears into them, never to return or be observed again from the outside. Despite decades of study, black holes remain among the most genuinely mysterious objects known to exist anywhere in the universe. Even though black holes trap light, scientists have been able to indirectly detect and even photograph the region immediately surrounding them. While the black hole itself remains invisible by definition, matter swirling around it before crossing the event horizon heats up dramatically due to intense friction and gravitational forces, emitting light and other radiation that telescopes can detect. In a landmark achievement, astronomers were able to combine data from telescopes around the world to produce the first ever image of a black hole's shadow, a dark circular void surrounded by a glowing ring of superheated material. This remarkable image offered humanity its first direct visual evidence of one of the universe's strangest and most theoretically predicted phenomena, finally becoming visible after existing only in mathematics and theory for over a century. The universe itself is expanding, meaning distant galaxies are gradually moving farther away from us over time. Observations of distant galaxies show that nearly all of them are moving away from our own galaxy and from each other, with the rate of this apparent movement increasing the farther away a galaxy is located. This expansion was first clearly identified through the work of astronomer Edwin Hubble, and it remains one of the most fundamental and well-supported findings in modern cosmology. Rather than galaxies moving through a fixed space, the space between them is itself gradually stretching and expanding, a concept that challenges everyday intuition but is strongly supported by decades of accumulated observational evidence collected across the entire history of modern astronomy. The light from the most distant galaxies we can observe left its source billions of years ago, offering a direct glimpse into the early universe. Because light takes time to travel across vast distances, observing extremely distant galaxies effectively means looking back in time, seeing them not as they exist today, but as they appeared billions of years in the past, sometimes not long after the universe itself began. Powerful telescopes capable of detecting extremely faint, ancient light have allowed astronomers to observe galaxies from remarkably early periods in cosmic history, offering direct observational evidence about how the universe looked and behaved during its earliest, most formative stages, long before our own solar system, our own galaxy, or anything resembling life as we understand it had even begun to exist. The universe is estimated to be approximately 13.8 billion years old, based on multiple independent lines of scientific evidence. This age has been calculated using several different methods, including measurements of the universe's ongoing expansion rate and detailed analysis of the cosmic microwave background radiation, a faint remnant glow left over from the universe's extremely early, hot, dense state shortly after its formation. Multiple independent methods converging on remarkably similar age estimates give scientists considerable confidence in this figure, despite the almost incomprehensible scale involved. Standing beneath the night sky, you are looking outward into a universe that has been quietly unfolding, expanding, and evolving for nearly 14 billion years before your own brief moment of existence arrived to look upward and wonder.
About it. Our sun is roughly halfway through its expected lifespan, meaning it has already been shining for about as long as it has left. Stars like our sun typically remain in their stable hydrogen-fusing phase for approximately 10 billion years before their internal fuel supply begins to run low and their structure starts to change dramatically. Current estimates place our sun at around 4.6 billion years old, meaning it has roughly another 5 billion years remaining before it begins to swell into a red giant and eventually transitions through the later stages of stellar evolution. This places our own sun, the very source of light and warmth that makes life on Earth possible, comfortably in what might be considered stellar middle age, still steadily burning through the long, stable middle chapter of its extraordinarily long life.
Eventually, in billions of years, our sun will expand into a red giant, potentially engulfing the inner planets of our solar system. As the sun eventually exhausts the hydrogen fuel in its core, physical changes will cause it to expand dramatically, potentially growing large enough to engulf Mercury and Venus, and possibly reaching all the way to Earth's orbit, depending on the precise details of how the expansion unfolds. This transformation, while occurring on a timescale so distant it holds no practical relevance to any currently living thing, represents the natural, well-understood evolutionary path that stars similar to our sun eventually follow. A slow, inevitable transformation written into the basic physics governing how
Stars like our own live out the full arc of their extraordinarily long lives. Some of the stars in the night sky belong to star clusters, groups of stars that formed together from the same original cloud of gas. Star clusters, such as the easily recognizable Pleiades, consist of stars that formed relatively close together in time and space from the same collapsing nebula, and which remain gravitationally associated with one another, at least for a portion of their lives. Observing a cluster offers a unique kind of snapshot, a group of stellar siblings, born from the same material at roughly the same cosmic moment, still visibly clustered together in the sky many millions of years later. Over enormous stretches of time, gravitational interactions with the rest of the galaxy will eventually pull most clusters apart, scattering these stellar siblings across vastly different regions of the galaxy. But for now, in this moment, they remain gathered together, visible as a tight, recognizable grouping against the broader backdrop of surrounding darkness. The universe contains far more matter that we cannot directly see, called dark matter, than the ordinary matter that makes up stars, planets, and everything visible to us. Based on the gravitational effects observed on galaxies and galaxy clusters, astronomers have determined that a substantial majority of all matter in the universe does not emit, absorb, or reflect light in any way we can currently detect directly. This mysterious substance, termed dark matter, appears to interact with ordinary matter primarily through gravity, shaping the large-scale structure of the universe, despite remaining fundamentally invisible and largely unexplained. Its presence means the night sky, vast and richly populated as it already appears, represents only a small visible fraction of everything that actually exists, scattered throughout the cosmos surrounding it. Beyond dark matter, an even larger and more mysterious component called dark energy appears to be driving the accelerating expansion of the universe. Observations of distant supernovae revealed something unexpected. The universe's expansion is not merely continuing, but actually accelerating over time, a finding that led to the theoretical concept of dark energy, a mysterious force or property of space itself that appears to be driving this ongoing acceleration. Current estimates suggest dark energy may account for a majority of the universe's total energy content, despite remaining almost entirely unexplained by current physics. This means that even the fundamental behavior of the universe's continued expansion, the very stretching of space carrying distant galaxies ever farther apart, remains rooted in a phenomenon scientists can measure and confirm, yet still cannot fully explain.